So inverters, also known as DC to AC converters, converts DC power to AC power, right? The same things can also convert AC power to DC power, right? So they can also be used as rectifier. How they get used as rectifier we learn a little bit later, but for now we will only see in a very simple way how to convert a DC voltage, a DC supply into an AC supply. As we start doing it, I request if you can stop doing the other work which you have been doing so that you can focus here. Okay. So the simplest one which you may already be aware of is if you have a DC voltage, right, you already know of this type of inverter, probably you would have seen it somewhere. Have you seen it before, this image? How many of you have seen this kind of inverter before? 40% of the people. Where did you see it? In course? H-bridge, yeah, but where did you see it? Like in some course? No? 103? Okay. Yeah, so this is a inverter, it's a single phase inverter, so it converts a DC supply into a single phase AC supply, right, the output which is an AC output. These four are the four switches. Again, you know, these are semiconductor switches, so they could be MOSFETs, they could be IGBTs. Let's just put them S1, S2, S3, S4. And this guy is called a this is a single phase inverter, right? It's this specific topology of a single phase inverter is also called as H-bridge inverter, and you can see the name, the H-bridge actually stands for this kind of a structure. So later on also wherever you see this structure of switches, you call it H-bridge. It's also called as a full bridge inverter. Okay, that's another name for it. How does it operate? Right, so you have four switches, so you can, you know, turn on some switch, turn off some switch, and then when in some combination you will get a certain output voltage, in some other combination you will get a certain output voltage, right? So we will just define all these possible combinations of switches. We also call these things as states. So all these combinations of switches, right, which we will write down now, we also call these things as states. States is a generic word, you would have used it in other courses also in different contexts, but here we call these things as state of the inverter. So when I write 1 means a switch is on, 0 means a switch is off, right? So you have 4 switches, 2 combinations of each. So you have how many states total? 2 into 2 into 2 into 2. How much is that? 16 states, right? Since we don't have sufficient space to write 16 states, we'll try to eliminate a few states, right? Which states do you think we can eliminate here? Is that okay? Does it make sense? Did you hear him? At the back? No. So he's saying you can eliminate the state when S1 and S2 both are on, or where S3 and S4 both are on. Right? Why do you eliminate those states? Anyone from the back? Anyone? Why do you eliminate those states? Why can't I turn on both S1 and S2? It won't be? But why? Why don't you turn on S1 and S2? Next person. That will be short circuit, right? Your DC will be short circuited. Right? So you can never turn on these two switches together, you can never turn on these two switches together, right? So out of 16 states, this would eliminate quite a few, because now these has to be complementary, this has to be complementary, right? So if you decide the condition for this switch, this automatically will get fixed and vice versa. So you have two combinations here, you have two combinations here, right? Of course, you can keep both of them open as well. Here also you can keep both of them open as well, right? So let's say out of 16 few we have eliminated. Now let's come to this open kind of a state. So when you open both of these, right, what happens to this point? This point is neither connected on the top nor connected at the bottom, correct? But as we would see that in further circuits you will have inductances, right? So you cannot open both of them, and therefore one of them have to be always turned on, right? You cannot keep both of them open. And this again, eliminates quite a few states, because you cannot keep these two open together, neither can you keep these two open together. Is that fine? Is that part okay? So a lot of states get eliminated, so only option left is this is on, this is off, vice versa, and this is on, this is off, vice versa. So two states, because of these, 2 into 2, total you have 4 useful states out of this 16 states. Okay, what are those 4? S1 1, then this has to be complementary. If this is 1, this has to be complementary. I can keep this, toggle this, I can toggle this, keep this, toggle both. Is that fine? Any doubt? Sorry? Why are you saying S1 and S3 cannot be on together? How is that short circuit? S1 is this, S3 is this. This is S2. So if I turn on these two, this is not a source, this is a load. So if maybe there may be an inductance, for example, its current will freewheel from here. This is the output. You get the point? This is the output. This is the source. Here maybe there is an inductor, maybe there are some R resistance, maybe RL combination, maybe RLC combinations, a few other things, right? So for now it's okay, you can think of it as just this one. This is open, you want to see what you can produce at the output voltage, converting DC voltage to AC voltage, right? So S1, S3 you can turn on together, there is no problem. Is that fine? S1, S3 you can turn on together, there is no problem in that. As long as you don't have a voltage source connected directly at V0 point, right? Most of the cases, as we would see, you have this inductor in series with it, right? And therefore, it's never a problem turning on S1 and S3 together. So now, if S1 is on and S3 is on, what is V0? V0 is 0. Second state, what is V0? Second state, what is V0? VDC? Second state, 0 or VDC? Because this switch is on, S4 is on, right? And S1 is on, this is on. So that means this point is connected here. So the plus point is connected to the positive of the DC source. The minus point is connected to the negative of the DC source. So the voltage appearing across V0 is nothing but equals to the DC source, right? So second is VDC. What about the third case? Minus VDC. And what about the fourth case? Fourth case? Okay. So these two things, we call it as zero states right? So these two things we call it as zero states, and these two we call it as active states. Right? Zero states because output voltage is zero, moreover this is disconnected from the output side in a way, right? Active state means this is actively connected to the output, and think in this way. Any question? Okay, so now if you have to use these four states and you have to produce an AC output voltage, right? You can do multiple things. You can, I mean, ideally what you want at the output is, let's say, something like this. Okay, let's say this is what you want at output. So if this is what you want at output, you understand that in this region, in the first region, you want a zero state, right? You want a zero state. Here you want an active state with plus VDC. Here you want another zero state. Here you want another active state, and here you want another zero state. Okay, you know how you can produce plus VDC, an active state, by using this switch combination. You know how to produce an active state with minus VDC. And for the zero states, you can either use the top one, or you can use the bottom one, or you can use sometimes the top one, sometimes the bottom one, right? But using these four combinations, you can create an AC voltage like this. Let's write down what are the switches which are conducting in each of this duration. So when active positive state means S1, S4 are conducting. When active negative state means S2 and S3 are conducting. Right? Now the question is, in these zero states in between, which zero state you want to use? The first one or the fourth one? We should idle in between. We should, okay, so maybe for some duration we use this, some duration we use this, right? How do we decide? The objective is that, as now we understand, right, for each switch to turn on and the other switch to turn off, right, requires losses, or it would lead to losses. So you don't want to do too many switchings, right? You want to minimize the number of switchings. So for example, if you see from going from here to here, you have S1, S4 on, and now you anyways want to do completely S2, S3 on. So you can do both ways. You can either first turn on S2, S4 and then these two, or you can first go to this and then this one. So you can use any state here. It would still require one switching at each transition, right? But then if you only use one of the zero states, then let's assume we are using only S1, S3 as the zero state, right? Then a lot of current is flowing through S1, S3. So the RMS current flowing through S1, S3 becomes more. Why? Because S1, S3 will be conducting during zero states also. Anyways, S1 is conducting during active state also. So as compared to these two switches, if you use zero state, this one for all duration, this will have more RMS current. They are all identical switches, right? There is no point in stressing more to only a few switches and let the other switch relax more, right? So you like to distribute these things equally. So maybe in one of the zero state you use something, this you use something else, this you use the same one. This is anyways, so this period and this period would usually be same, right? I have not drawn it that way, but these would be same. So you can use, let's say, one zero state Z1 in these two, in these two, because this is continuous, right? So Z1 to Z1 is continuous and this whole duration is continuous. You can use something like Z2. So there is no point in switching between zero states unnecessarily to, that would lead to increased losses. Any questions so far? Yeah, it works properly. You can, I think so, you can keep anything on any side, that should be okay.
use S1, S3 as previously was already mentioned. Then S1 would be all for most of the that we don't have to turn off S1 only during S2, S3 actions.
Yeah. Okay, you mean switching losses? Yeah, there are two losses, right? One is switching loss, one is conduction loss. So, okay, let's try. So, you are saying you want to use only the first state S1, S3. So, hypothetically S1, S3 here, S1, S3 here, and S1, S3 here. That's what you mean? In one, this is a power cycle, right? This is 20 millisecond. In 20 millisecond, how many times S1 will switch? Turn on and then turn off. Once, it will turn on once, it will turn off once. S2, S3, S4, same. Right? If you don't use this sequence, if you replace this one with S2, S4, still the same. Right? So, the switching losses will remain the same. Only thing is now your stress is not only on the two switches in terms of the RMS current. So, the conduction losses is in a way getting divided also, because finally you have to cool these devices down and so on, right? So, a lot of those challenges. So, we can use S2, S4. Any more doubt? If you want to change the magnitude of the output voltage of the AC voltage, right? Can you do that? Yeah. No, you just change this width, make these two things wider, your RMS value will go up. This case, very simple. You can, in this picture, it's very simple, right? You just increase this duration, right? You, in your microcontroller, you make sure this PWM, this gating signals are small, this gating signal is large, and that would do the job. Isn't it? What is the maximum RMS that you can produce? What is the maximum RMS of this waveform that you can produce? VDC. Right? You can have this full thing, like you can do this maximum, right? There is no zero state. So, maximum RMS you can produce is VDC, but you can produce anything less than VDC also. Yeah, so in a way you can produce, if theoretically speaking, very, very small voltage also. Right? So, you can keep reducing the voltage. So, it's not a, let's not call it a buck converter or something, but you get the idea, right, that the output RMS voltage is limited by the supply DC voltage, and you can always produce smaller than that. You cannot produce more than that in this kind of circuits. So, yeah, it's not a buck converter, but you get the same sort of feel here, right? So, V output RMS max is equals to VDC. Okay, now another question. If you see this picture, I have drawn this duration same as this duration, right? And again this duration same as this duration. So, any reason for doing that? Why can't I sort of, just, place one guy here, or randomly? Why I am trying to place it in this structure on this way? And that's also AC, right? I mean, of course, let's say I bring this guy to this corner, durations are the same. I take this guy to some other corner, or I let it in middle, why can't you just randomly place them? The RMS value will be the same, right? Still an AC. So, why did I draw it like this? Together. ठीक है, need not bring this guy to this edge, but little bit ahead of the edge. But what I am saying is they need not be, why I have drawn them to be symmetric. They need not be symmetric. As of now, the way I have drawn it, at least in my mind, I have kept this as T1, this as T1, this as T1, this as T1, right? So, if you ask me to increase the magnitude, I will increase it, all the 4 T1s will reduce so that everything is symmetric. But I could have had this as T1, this as T2, this as T3, that other one as T4, neither of them equal to each other, right? It still be AC, still the same RMS, correct? But then why should I care about it in this context? You're right. You're perfectly right, right? That you wouldn't have a... No, you would have single frequency. What do you mean by you won't have a single frequency? Oh, you can draw, you can do the Fourier series, you will get the expressions. So what he said is right, that by drawing it in a symmetric way, you eliminate these even harmonics, right? This is what we saw in the last lecture. So that was the whole idea of introducing you to the Fourier series, because now we'll be using it. Drawing it symmetric, you eliminate the even harmonics. Now why do we care about that? I'll give you an example. Let's say this voltage, right, you produce using this inverter. What will you do with this voltage? What is the application? Can you think of some application? What should I use it for? Let's say I have a box where I convert a supply from DC to AC. Now what do I use it for? Okay, I can use it for some sort of an induction motor, right? This is a single phase, maybe single phase induction motor, maybe I can have a 3-phase version of it, 3-phase induction motors. Now if you see in induction motor, if I do a 3-phase induction motor, it would have, if you supply this voltage to it, it would draw some fundamental current and it would also draw harmonic current. And the motor will not work as smooth as you want it to work, because it has a sinusoidal component, it's rotating, because the sinusoidal will lead to a rotating flux field which is also sinusoidal. But now there are these other harmonics also which would try to play around in that flux field and would create some sort of a oscillatory or jerky motion of the motor. I don't know if I told you that, but you would have observed it, you may not have observed it, but if you use a home inverter, right, and if the electricity goes off, and if that home inverter supplies to your loads, right, then you can notice a sound comes out from the fan, which was earlier not present when you are getting supply from the grid, right. I keep mentioning it, but I think over a period of ages, this thing becomes lesser and lesser relatable, because now, of course, you don't have so much of power cuts, you may not have seen those inverters which I am talking about, you may not have experienced it. But anyways, I think some of you can and still correlate. You have not heard the sound, okay. So that's another thing. So again, I'm not able to relate because of the time gap. So I'll tell you why you didn't hear the sound also. So you didn't have this kind of an inverter giving this voltage, right, which we'll come to later on. But if you have a basic inverter, the most cheapest one, right, then this is the output it gives. You connect to the fan, it works, it rotates, of course. There's a sound, it's not only the sound, internally there is a torque oscillation also happening in that, right. You are losing efficiency, your torque is jerky, so you don't like it. So the objective is to minimize as much harmonics as possible. So at least, we can, without putting much effort, we can at least eliminate the even harmonics just by, making it symmetric. So that is the simplest thing at least you can do without really putting too much effort. Of course, we do much more than that after it, which we'll learn a little bit later, maybe post mid-sem. We do a lot of efforts of further eliminating harmonics from this waveform, right? But least what you can do here is make it symmetric. So that's the idea. For half wave symmetry, only T1 and T1 and T3 should be equal. T1 and T4 should be equal and these two should be equal. Correct, but so if these two should be equal, these two should be equal, you can have this little bit broader, you can have this little bit broader. Is that what you are saying? Or you can shift this way inside also. That's true, that will reduce the fundamental component is my guess. I have to solve it and check. My guess is it would reduce the fundamental component RMS. It will not reduce the total RMS. Total RMS will remain the same, of course, right? But when you find out the fundamental component RMS, why will you find out fundamental component RMS is, you understand what I mean by fundamental component RMS? Yeah. Siko. So this has multiple frequencies, right? If you just take the fan example again, right? Actually you are only utilizing the fundamental component because other harmonics are creating these oscillations, vibrations, right? They are of no use. So the main component which is being used is the fundamental sinusoidal which is there, right? You cannot see it, but which is there, because you can visualize it like this. There is a fundamental component which is there, right? So the fundamental RMS would matter more than the total RMS, and we will eventually see that. So even though the total RMS will remain same, my guess is the fundamental RMS will be maximum this way. But maybe you can verify. I'll also try to check. If maybe you can remind it again next lecture, we'll try to take over. Sorry?
It makes sense to me that.
Yeah, I also feel that, but you can check. Anyway, it's not costing us anything to make it symmetric, huh? So we are not losing anything. Okay, any other doubt? Because you want to eliminate the harmonics anyways, so you have to put a lot of effort. What is those efforts? Maybe you will do something with the switching signals, maybe you will install a big filter. If you can just eliminate something by doing as simple as just placing these asymmetric values, why would not you want to do that? Any other question? Any questions? Okay, if there are no questions, let's move on to this is another inverter. The one on the left was, or what we saw before was called as full bridge, edge bridge. This is called as half bridge. Right? In this case, unfortunately, you don't have any zero state. Right? Both states are active states. You can have plus, you can have minus, you cannot have zero. Plus is not, instead of plus VDC, now it is plus VDC by 2, minus is minus VDC by 2. Right? Anyways, now there are two switches, you know you cannot open them both, you cannot close them both. So you have only two states, right? 1, 0 or 0, 1. One will give you plus VDC by 2, one will give you minus VDC by 2. Okay? You would require two DC sources of, so for the total VDC, let's say earlier we had a total DC link voltage of 400 volt. You could have produced an output with an RMS of 400 volt. Now if you have 400 volt in this circuit, your output RMS maximum can be 400? 200, right? Because now your waveform is maximum 200 here and 200 here, so the maximum or the RMS itself is 200, right? So with the same DC source, you could have had more output voltage RMS in full bridge as compared to half bridge. Is that okay? Is that fine for you? Again, if you see in one cycle switch, there are only two switches, S1 and S2. So S2 turns on once, turns off once, S1 turns on once, turns off once, right? There's only S1 will turn on once because when you have this state, then S1 is on. When you have this state, then S2 is on. So S1 is turning on here, turning off here. S2 is turning on here, turning off here. So in one power cycle, one fundamental cycle, this is, we'll use different words. So this is power cycle. This is, we also call it as a fundamental cycle. We also call it as a 50 Hertz cycle. Just In reality it may be 50, 51, but they just want to call it 50 Hz cycle, which is nothing but equal to 20 millisecond of time. So in one power cycle or in one fundamental cycle, your each switch will only switch once. Okay, any doubts so far? Any question? Any doubts? Anyone? Somebody wanted to ask something from here. Go ahead. Oh, we have problem with all the harmonics, not just even harmonics. We don't like any harmonics. We only want to have a pure, nice sinusoid 50 Hz fundamental frequency. That's it. So we want to eliminate them whichever way possible, whichever is easiest for us. So as soon as we get the opportunity, we eliminate them, right? Okay. Any doubt from here? Any doubt? Any question? Now, you may be thinking that why are we even seeing this? Gives you half the output voltage. Why would I use it? Anyone thinking this way? No, this is full bridge. Gives you 400 volt RMS output. This gives you half the RMS output. Why would I even want to use this? Of course, you can get it from there also, yeah. But what I'm saying is, it seems like it's restricted, right? I mean, why would you want to use this? Okay, yeah, that's true. You only need two components now. So, direct, if you see the mapping, the number of components is less, right? That's the advantage. The other disadvantage you may feel for now is here your output voltage is adjustable, here it's not adjustable, right? That disadvantage will go away when we look at a different way of modulation. So what we are seeing now in both the boards is what is called as fundamental modulation. What is the meaning of this word? The meaning of this word is that each switch is switched once in power cycle. Each switch is switched only once in a power cycle. That is what we call it as fundamental modulation. Here also we saw, S1 is only turning on once, turning off once. It switched once. Here also all the switches turn on once, turn off once, right? In future we will see some other types of modulations. That means the structure will remain the same. But this turning on and turning off business, we will try to do it in different ways and different fashions, which will give us more benefits as we move forward. We will look at it. These are like very basic things. These are called as fundamental modulation. The circuit will remain the same. I'll repeat. Only thing is modulation means, the word modulation here means that how we are turning on the switch, how we are turning off the switch, when to turn on, when to turn off. That is what we mean by the word modulation here. Fundamental, of course, you understand means the power cycle. So fundamental modulation means you are turning on and turning off the switch once per power cycle. Is that okay? Good. Okay, I wanted to also talk about three-phase inverters, but I see the clock now and I feel that we should do the assignment and the three-phase inverter part maybe we'll do after mid-sem then.